So vector v, let's say vector v is, I think I'm going to work in R2 for this example. If vector v is the vector 2, -3, then 2 times vector v is 2 times the components, 2 times 2 and 2 times -3. So that will result in 2v being equal to 4, -6. Let's take a look at what that looks like graphically. I'll graph vector v in blue, and we have 2, -3, so I have 2, -3. Vector v is going to look like this. And I'll graph vector 2v in pink. Vector 2v is 4, -6, so that's going to look something like this. Didn't quite get those lined up there. You can still see v here. And 2v in pink is twice as long because I've taken the vector v and I've multiplied it by 2. So that's what the geometrical interpretation of scalar multiplication means. It's how does this operation that we do on a vector manifest, if you will, in the graphical comparison. In the algebraic comparison, I can see that the components of v, I'll do it this way, the components of 2v are twice the components of v. And so on the graph of 2v is twice as long as the graph of v. In other words, scalar multiplication scales the vector. So one of the reasons it's called scalar multiplication. It scales the vector, it stretches it or it shrinks it. Let's do another one. I'll still use v. Let's go with 1/3 v. Algebraically, that's going to look like 1/3 of 2 and 1/3 of -3. And I'll do that one in yellow. Let's see, 2/3 is going to be about here, and -1 is here. And when I graph that, I get that vector there, that yellow vector, which is 1/3 of the length of vector v. Not surprisingly, since this scalar has scaled vector v by 1/3. Let's do one more. This is something I left out. Let's take a look at -3 times vector v. And again, algebraically, this is going to be multiply each of the components of vector v by -3. So I'll get -6 and +9. And I'm going to do this one in green. I need to add some tick marks. I need -6, so 1, 2, 3, 4, 5, 6, and +9. All the way up there. And that vector, oh, I need green. That vector will look something like this. What's happened in this case is not only has vector v been scaled by 3, as you can see the green vector here is 3 times the length of vector v, the blue vector, but it's also reversed the direction. The negative reverses the direction. So that's something else to keep in mind. I could, in fact, I'll just do one more. Negative, that's not the color I want. Negative vector v. If all I do is negate vector v, I'm negating the components of vector v, I'll get -2, 3, which is -2, 3 is about there. I'll get this vector here. And that vector is the same length as vector v. I could slide a 1 in there if I wanted to. It's the same length as vector v, but it's going in the opposite direction. So this negative in front reverses the direction that vector v is going in.